So, what is SAT? SAT in logic and computer science is called a Boolean satisfiability problem. I like to call it propositional satisfiability problem because then I remember that SAT is just about propositional logic, but most of the times you are going to find it as like abbreviated as SAT, since it's like the way the problems are defined in complexity theory and where SAT comes from. So the SAT problem is the problem of deciding if there is a solution for a given problem that satisfies this propositional logic formula that we are evaluating. So in other words, you have like a formula that it's written using propositional logic quantities, and we ask if there is a way to have inputs into this formula that it will evaluate to the final formula to true. The way we do it is basically very, very, very inefficient. And that's why the SAT problem is the first problem, in fact, that it was proven to be NP complete. NP complete just means that someone, or better, no one knows an algorithm that can efficiently solve a problem. So it means we cannot solve the SAT problem in an efficient way right now. So we don't know an algorithm for it. About SMT, you can think about it like an extra layer that are added on top of SAT problem that adds to this whole tag a bit vectors, arithmetic support, and arrays. So if you think about SAT, we can just use it with propositional logic quantities, with SMT solvers. We can also just use like plus and minus and multiply vectors. We can even build bit vectors and build arrays that may say in a pretty similar way as we have it in let's say normal programming language or more common programming language. The SMT solvers, they allow us then in a very rustical way for us to encode the same problems in a more efficient way. So we don't need to translate our plus and minus into ands and ors. And in this way, the solvers understand it better, the structure of the problem that we have, if we can use the same functions and ideas that we have from a more abstracted way than a simple propositional logic. But SMT and SAT and all of this kind of set-based formal methods, they rely a lot on the concept of constraints. So what are constraints? Constraints are just like limitations on boundaries that you have. It doesn't matter how, it's just like a definition. Eugen Freude stated in 1997 that constraint programming is almost like the holy grail of the programming concepts, because until then we basically had this kind of programming languages that worked like writing a recipe. So we would write a program because we had a problem, like I want a cake, and to have a cake in the end of like a return of that function, I needed to tell the program, like actually write an algorithm that would bake that cake for me. So I needed to state how many eggs and how much milk and all this, and in the sequence that it's supposed to do each step, so that it would return the cake for me. And the idea of constraint programming is that you tell the computer that you want a cake, and then you tell the computer what's in your kitchen. And the computer will tell you if it's possible for you to bake the cake with the stuff that you have in your kitchen right now, or if you need to do some groceries before. And if it's possible to bake the cake in your kitchen right now, it's going to give you all the solution, also like the recipe. And these kinds of make the computer actually what we expect it to be, a problem solver. We don't need to solve the problem anymore. We just need to have a problem and give the limitations that we have right now, or constraints. But the way that a SAT works with these constraints are, as I said, not very efficient. We are going to do it with pen and paper just to have an idea how most of the SAT solving algorithm works. And for doing that, we start with this propositional logic equation, and we are going to solve with the same steps that a SAT solver would do. So we consider this. And the first thing that we need to do is evaluate which are our inputs. And we have A, B, and C in this case. So what we do, we build a table and we write all the possible permutations that we have for A, B, and C. 0 being like false and 1 being true. And the next step is, at least the way I think it's easier to solve this kind of problems, is breaking it into smaller pieces. So what do I do is, now I know I defined A, B, and C possible inputs and permutations of it. And then what I do is like I get the first part of the equation, N and B, and I put it like in a column. And then I check the next one, and it's not B, it's the next column. And then I need to solve B, not B and C, and it's the next column. And then I have the whole equation that it's going to be the answer for my truth table. That's the name of this table that we are building right now. So as we defined it, we can start solving it. So the first one is an AND connector, which means that we need to have A and B valid to have a valid A and B. So what happens here is, for example, if we have A is false and B is false, N and B are also going to be false. The same is valid for A is false and B is true, because just one of it is true. And so, as you can imagine, we have the same for A is true and B is false. And we are just going to have it set to true if A and B are true. So that's pretty easy to remember. The next one was the not B. So not B is also not that hard to remember, because we just need to invert the value that we have in B. So if B is false, not false means it is true. And that's what we have here. And if we have B set to true, not true is going to be false. And that's what we do for all our truth table, or all the cases that we have here. So the next one is not B and C. So we are going to get the not B that we just reasoned about, and then we get the C from the first column. So if we have not B true and C is false, we are having false because it's also an AND connector. And then if we have not B is true and C is true, so we have true and true is going to be true. And then we have the last one. So our last one is the whole equation that has in the middle the OR. The OR is going to work also not that hard. We know that like in the first part of it we have a false, the second part is false. So we have false or false is going to be false. But in the case that we have false or true, it's going to be true because we just need one. And we go through the whole table. So now that we solve it, the question here for the exercise of the training is we consider the same equation that we have right now on the display, and we set A, B, and C, all of them to true. What's the answer that we have for the truth table?